Okay, today's lesson is about related rates, and related rates mixes word problems and implicit differentiation. So related rates just happens when there's more than one quantity changing with respect to time in a problem. Let's go ahead and dive into example 1. There's a hole in the cylindrical grain silo up the road, and it is pouring out at a rate of 2 cubic feet per second. The tank stands 40 feet high with a diameter of 18 feet. At what rate is the height of the grain changing when it is 20 feet high? So sketching our cylinder, the silo is 40 feet high. Its diameter is 18 feet. Inside the cylinder, there's a column of grain that's also a cylinder shape, and it has a height h. The grain is pouring out at 2 cubic feet per second. That's actually a rate of change of volume. Look at the units, cubic feet per second. So we're going to call that rate dV/dt. And since the grain is pouring out, the volume of that grain column is decreasing at 2 cubic feet per second. We're also talking about a height in the problem. I'm not going to plug in a value for height yet since it is a variable, it's changing. And it's also mentioned in diameter. I'm not going to write down D just quite yet. But let's go ahead and write down the formula for the volume of a cylinder. So the volume of a cylinder is pi r squared h. So in a minute, we're going to be taking the derivative of this equation. But first what I get to do is I get to plug in any values that remain constant during the entire problem. So the radius of this grain is not changing. It's staying constant. So since the diameter is 18, the radius is going to be 9. So I'm going to go ahead and plug in 9 here for radius since that stays constant the whole time. So my formula is going to be 81 pi h. And I can go ahead and put units on there. It's feet squared. Those are my units so far. Okay, so what I'm going to do is I'm going to take the derivative of this and then I'm going to go back and plug in my dV/dt, and I'm going to plug in that h is equal to 20. I don't really care about the dimensions of the actual silo, so I'm going to cross those out. What I care about are the dimensions of the grain itself. So differentiating, my derivative is going to be dV/dt. Over here, this 81 pi in feet squared, those are all like constants or units, so I don't need product rule. So just differentiating, I'm going to get 81 pi. I'm differentiating with respect to t, so I'm going to have dH/dt. And then that feet squared is kind of like a constant. The units just go along when I differentiate. So let's go back and read the problem. At what rate is the height of the grain changing when it's 20 feet high? So what they're actually asking us to find in the problem is dH/dt, the rate of change of the height. So let's plug in. So we have negative 2 feet cubed per second is our dV/dt. That equals 81 pi. There's nothing else to plug into, so I can just go ahead and proceed with solving. So to get dH/dt by itself, I'm going to divide by that 81 pi feet squared. Actually, instead of dividing by feet squared, let's just cancel feet squared out of both sides. So canceling out that feet squared is going to reduce that cubed to just feet per second. So dividing by the 81 pi, I get negative 2 over 81 pi feet per second. So let's take a look at our answer. Should dH/dt be negative? Yes. Since the height of the grain is decreasing, negative is an appropriate sign for our rate. And feet per second, would that be an appropriate unit for the rate of change of height? Yes, because our height is measured in feet. Example 2. The top of a ladder, 10 feet in length, slides down a wall at 0.5 feet per second. How fast is the base of the ladder moving away from the wall when the top of the ladder is 8 feet above the ground? So let's get a little picture going here. Here's our ladder leaning against the wall. It's 10 feet in length. And it's the top is sliding down the wall at 0.5 feet per second. And we want to know how fast the base of the ladder is moving away from the wall when the top of the ladder is 8 feet away. So at some certain point in time, this is going to be equal to 8. So this is a triangle problem. We have to think about what do we care about in the triangle? Do we care about the angle measures in the triangle? No, it doesn't talk about angle measures at all. Do we care about the area of a triangle? No. But what we do care about in this problem is the side lengths of the triangle. So this is a right triangle, since the floor and the wall are at right angles to each other. So what we know that relates the sides of a right triangle is the Pythagorean theorem. So we can first plug in anything that remains constant in this equation. So A, let's go ahead and label this side of the triangle A. Let's label the base B. So as the triangle slides down the wall, both A and B are changing. So we cannot plug in any values for them because they do not remain constant. However, the height of the ladder remains constant. We don't need to plug in units in this problem. You'll see why in a second. So now we can differentiate with respect to time. So taking the derivative of A with respect to time, we're going to get 2A dA dt plus 2B dB dt. Time squared is a constant, so its derivative is 0. So this is very similar to implicit differentiation, where when you take the derivative of y, you have to multiply by dy dx. Any variable you differentiate with respect to t, you have to multiply by like dA dt, dB dt, etc. Let's go ahead and see if we have all the information we need to start plugging in. So looks like we have A. A is going to be 8 feet. We have dA dt because that side of the ladder is sliding down at at 0.5 feet per second. So A is getting smaller by negative 0.5 feet per second. Let's go to the question. How fast is the base of the ladder moving away from the wall? So dB dt is what we're trying to find. And they don't give us B, but we can easily find it. So if we know the Pythagorean theorem, we can set up the Pythagorean theorem and find B. And B is going to come out to be 6. If you use Pythagorean theorem, you get 6 feet. But also some common Pythagorean triples. So some common Pythagorean triples that you might need are 3, 4, 5. If you double all of those sides, 6, 8, 10, that's a Pythagorean triple. If you triple the sides, 3, 4, 5, that's also a Pythagorean triple. 9, 12, 15. 8, 15, 17 is another common Pythagorean triple because 64 plus 225 equals 269. So that is another Pythagorean triple. And then there's one more. It'll come to me when we do another problem. There's another common one that we might be using. So now that we have all this information here, let's go ahead and plug in. So 2 times 8 feet and I told you the units don't matter on that 10 because when we differentiate the right-hand side, we just got that 0 anyway. So let's multiply here. So negative 0.5 times 8 is negative 4 times 2. So we get negative 8 feet squared per second. Okay, I'm going to do 2 steps at once. I'm going to move this to the other side and multiply. So I'm going to get 12 feet and then dB dt. And then dividing, I get, let's get rid of this. Dividing, I get -8/12. And then I cancel one of the feet out of both sides, so feet per second. Oops, when I move that 12 to the other side, it should become negative. So -8 divided by -12, it just gives me positive 8/12 feet per second for dBdt. Okay, so let's see if our units make sense. Since B is getting bigger, since the base of the letter is sliding away from the wall, our answer should be positive, which is what we got. And feet per second are an appropriate unit for the rate of change of that side length B. Billy put a cookie sheet full of Shrinky Dinks in the oven. You might get, hopefully we can make Christmas ornaments out of Shrinky Dinks, even remote learners. I will hopefully be able to get you guys Shrinky Dink material. We usually do that like the day right before Christmas. It's fun. One piece has a triangular shape. The base of the triangle is shrinking at 0.1 centimeters per second, while the height of the triangle is shrinking at 0.2 centimeters per second. At what rate is the area of the triangle decreasing when the base is 9 and the height is 1? So we have some triangular shape, and they tell us that the base is shrinking, so that would be dBdt. And since it's shrinking, I'm going to put negative. And the height is also shrinking. And the rate of change of the height is negative 0.2 centimeters per second. At what rate is the area decreasing? So dAdt is our unknown. They give us a base of 9 and a height of 1. So our previous triangle problem used Pythagorean theorem, and this one is talking about the area of a triangle. So we're going to use the area formula for a triangle. None of these quantities remain constant. A, B, and H are all changing. So we can't plug in anything before we take the derivative. But let's go ahead and differentiate, and we're going to have to use product rule since on the right we have a product here. Let's show t some respect. Differentiate with respect to t. Derivative of the first is going to be 1/2 dBdt times the second plus the first function times the derivative of the second. Now let's see if we have everything we need to plug in. So we want to find dAdt, that's our unknown. dBdt is given, and H, and B, and dHdt, yes. So everything we need to plug in is given. So our dAdt comes out to be 1/2, and plugging in. Okay, so 1/2 times negative 0.1, that's going to be, I believe, negative 0.05 centimeters squared per second minus 0.9. I'm just reducing these twos here, so I get negative 0.1 centimeter per second times that 9, negative 0.9 centimeters squared per second. So negative 0.95 centimeters squared per second. So if the base and the height are both shrinking, the area should be getting smaller as well. So negative does make sense for our sign. And centimeters squared per second would be appropriate units for the rate of change of area. The top of a 20-foot ladder rests on a vertical wall with the bottom of the ladder on level ground. The top of the ladder is sliding down the wall at a constant rate of 3 feet per second. So the side is sliding down at 3 feet per second. That side's getting smaller, so I'm going to put the negative. At what rate in radians per second is the acute angle between the top of the ladder and the wall changing? So let's call this theta. So our unknown is d theta dt. At the instant, the bottom of the ladder is 12 feet from the base of the wall. So at some point in time, this is 12 feet away. I'm not going to label my sides B, the base, and height, or A and B, because I'm not using Pythagorean theorem this time. Instead, since we're talking about radian measures, I'm going to use SOHCAHTOA. We're talking about the side lengths of the triangle and also radian measure the angles. So let's go ahead and take a look at theta. And this side opposite theta is the 12. So I'm going to call that side opposite. So the opposite side is 12, but not the whole time, just at a certain point in time. This side is 20, since that's our ladder. That's our hypotenuse. So I definitely want to plug in any constants before taking the derivative. So I definitely want to use the hypotenuse. So I'm either going to be using sine or cosine to create my equation. So let's see. And I need to use this side here. I need to use the negative 3 feet per second. And that's going to be the side adjacent. That's the rate of the adjacent side. That's by d adjacent dt is the negative 3 feet per second. So I definitely have to use the adjacent side, and I definitely have to use the hypotenuse because I want to plug in a constant, so I'm going to use cosine. So cosine of theta is going to equal the adjacent over the hypotenuse. And like I said, I definitely want to plug in that 20 because that's going to make my derivative a lot easier to take. So this derivative here is going to be negative sine theta d theta dt. And then on the right-hand side, we get 1/20th d adjacent dt. Taking the derivative of the adjacent side with respect to t. So now we're ready to plug in. So let's take a closer look at this triangle. I'm going to need sine theta. Well, sine is the opposite side and over the hypotenuse. So I have negative 12 over 20 is sine. D theta dt is what we want to solve for. And that equals 1 over 20 and then the d adjacent dt, which is that negative 3 feet per second. So simplifying, I can multiply both sides by 20, which gets rid of that 20. Let's divide that 12 to the other side, and the negatives cancel. So I get 3/12 feet per second. Oh, I forgot on these problems, you do not need to worry about the units. So we don't need to carry those units through. So it's just negative 3. So we just get 3/12, and our units is just going to be radians per second. So as the ladder slides down the wall, if you envision what's happening, so our triangle is going to be looking more and more like this as the adjacent side gets smaller, and theta would be getting bigger. So our d theta dt should be a positive value. A kite is being blown away from the person holding its string in a direction parallel to the ground at a rate of 10 feet per second. The height of the kite is 100 feet above the height at which it's being held. At what rate must the string be let out when the length of string already let out is 200 feet? So let's see what we have here. So we have some person holding a kite string, and the kite is being blown in a direction parallel to the ground. So the kite is being blown this way. And it says that the height of the kite is 100 feet above the height at which it's being held. And it's being blown in that direction at 10 feet per second. So again, it looks like we have a triangle problem. So are we talking about the area of the triangle, the radian measures, or the side length? Well, we're talking about the side length again, and this is our right triangle. And then the string, at some point, the string is equal to 200, not the whole time. So let's go ahead and label this A, B, and C. So we're talking about Pythagorean theorem. So A squared plus B squared equals C squared. It's being pushed out to the side at 10 feet per second, but it says nothing about the height of the kite changing. So from the information given in the problem, we can conclude that B stays constant. So this is our equation. Let's differentiate with respect to t. So 2a dA dt, the derivative of 100 squared is 0, equals 2c dc dt. Okay, so let's label the quantities and variables given in the problem. So A, I don't think we know A, but we can find it in a second here. They told us that C, the length of the string, is 200. dA dt, we know that's that 10 feet per second. I'm going to put feet with this 200. And dB or dC dt, that's what we're trying to find because it says at what rate must the string be let out. So dC dt is our unknown. We can find A by doing Pythagorean theorem. So we have 200, 100, and A. So A squared plus B squared is 10,000. That equals C squared, which is 40,000. So A squared is 30,000. A is the square root of 30,000. So if you want to simplify that, as you know, 10,000 is a perfect square. So we could factor out 10,000. And we would be left with 100 root 3 for A. Okay, so A is 100 root 3 feet. Oops, feet. Okay, so plugging in, and we have 2 times this A value we just found. I'm going to move this line out of my way. Okay, so we can do a little canceling now. So I'm going to cancel those 2's out of both sides. I can divide both sides by one of the feet, so those cancel. I can actually divide both sides by 100, and that gets rid of these 2 zeros here, and it would get rid of 2 of these zeros here. So on the left, we have 10 root 3 feet per second. On the right, we just have 2 dc dt, and so I'm just going to divide that 2 over to the left. So this 2 that's left from the 200 divides over to the left. So dc dt comes out to 5 root 3 feet per second. So is C getting longer? Yes, the string's getting longer, so dc dt should be positive, and feet per second are appropriate units for that rate of change of the string length. Last one in the street light problem. So a 6-foot tall man is walking toward a street light at 2 feet per second. If the street light is 16 feet tall, at what rate is the length of his shadow changing when he's 20 feet from the light? So let's go ahead and get a picture going here. So here's my street light. Don't judge, I'm not good at drawing these. And we have a man. The light is shining down on the man, and he is casting a shadow on the ground. So when he hits the man, this shadow is cast on the ground. That is not a body. That is a shadow. Okay, so it says the man is 6 feet tall. and the street light is 16 feet tall. So what we have here is we have overlapping similar triangles. It's kind of a picture of what we have. So we have our man here and our street light here. I like to call this S for the shadow length, and I like to call this D, this distance from the street light. So if we separate these overlapping triangles, the big triangle is going to have a height of 16 and it's going to have a base of D plus S. The smaller triangle is going to have a base of S and a height of 6. Now these are similar triangles by angle, angle, angle. These are equal angles because they're the exact same angle. These are equal angles because they're both right angles. And so that would leave these angles have to be equal since the angles in a triangle add up to 180. So those are similar triangles by angle, angle, angle. Let's go ahead and set up a proportion that relates the sides of these similar triangles. So 16 over D plus S. So the ratio of height to base equals the ratio of height to base equals 6 over S. So now that we have our proportion set up, let's cross multiply. So cross multiplying, we get 16S equals 6D plus 6S. And then that's not a 6. 6D plus 6S. Let's subtract that 6S to the other side. So we get 10S is equal to 6D. Now, we don't have anything that we can plug in that's remaining constant because as he's moving toward the street light, both the shadow length and his distance from the street light are changing. So we're differentiating without plugging anything in. So taking the derivative of the left, the derivative of S with respect to t is ds dt. And differentiating on the right, we get 6 d dt. So let's go ahead and see what we have to plug in. It says a 6 foot tall man is walking toward a street light. So as he's walking toward the street light in this direction, this distance from the light D is getting smaller. So d dt is negative 2 feet per second. If the street light is 16 feet tall, we already used that. What rate is the length of his shadow changing from when he is 20 feet from the light? We actually don't need to know how far he is from the light. And now we just need to find our ds dt because it says at what rate is the length of his shadow changing. So our ds dt is our unknown. So plugging into our derivative, we're going to get that 10 ds dt is equal to 6 and then the negative 2 feet per second. So dividing by 10, we're going to get negative 12 tenths feet per second, or negative 1.2 feet per second. So as he's moving toward the street light, his shadow is getting smaller. So that actually makes sense if you think about when the sun is directly overhead at noon, you have a very small shadow. But when the sun is lower in the sky in the evening or in the morning, you have a longer shadow. Same thing here. When the street light is further away, the shadow is going to be longer since it's kind of going to be at a lower angle to the person. So as he moves toward the street light, his shadow is indeed going to be getting smaller. So the negative sign makes sense for our ds dt. How fast is the tip of a shadow moving? So that's a different question. The first one we answered is what rate is the length of a shadow changing? So the shadow is getting smaller at 1.2 feet per second. How fast is the tip of a shadow moving? So there's actually two different things happening with the shadow. So as the man is moving to the left, he's taking his shadow with him. So he's moving 2 feet per second to the left. And his shadow is also moving with him at that same rate. But at the same time that he's moving at 2 feet per second in that direction, his shadow is shrinking at 1.2 feet per second. So that the head of the shadow, or the very end of the shadow, is not only being moved with him, but it's also shrinking. And those are like velocity vectors that we can add together. So if we add those, the tip of the shadow, right here, the end of the shadow is moving at 3.2 feet per second. The velocity at which he's moving plus the velocity at which, or the rate of change of the shadow itself.